Everything around you, the air you breathe, the ground beneath your feet, the water you drink, is made of the same fundamental building blocks. We call them atoms, and they are the smallest pieces of matter that retain the properties of a substance. But atoms themselves are not solid, indivisible spheres as scientists once believed. They are intricate structures, tiny universes unto themselves, where smaller particles dance in an elegant arrangement that determines what something is and how it behaves. Let's begin with the basics. An atom has three main types of particles. At its center sits the nucleus, a dense core containing protons and neutrons bound together by forces we'll explore later. Surrounding this nucleus in a cloud-like region are electrons, which orbit at various distances. These three particles, protons, neutrons, and electrons, are the essential characters in our story. Protons carry a positive electrical charge. They are relatively heavy, and their number defines what element an atom is. This is crucial to understand. If an atom has one proton, it is hydrogen. If it has two protons, it becomes helium. 3 protons makes lithium. The number of protons is so fundamental that we call it the atomic number, and it is the element's true identity. No matter what else changes about an atom, the number of protons determines which element you're looking at. Neutrons are similar to protons in many ways. They have nearly the same mass and also live in the nucleus, but they carry no electrical charge. They are neutral, which is how they got their name. Neutrons can vary in number, even for the same element. This variation creates what we call isotopes, atoms of the same element that have different numbers of neutrons, and therefore different masses. Some isotopes are stable, while others are radioactive and decay over time. Electrons are the third piece of this puzzle. They are far lighter than protons or neutrons, and they carry a negative electrical charge. They occupy space around the nucleus in regions called orbitals, though not in simple circular paths as older models suggested. Instead, electrons exist in probability clouds, regions where they are likely to be found. The way electrons arrange themselves around the nucleus determines how an atom interacts with other atoms, and this is where chemistry truly begins. Here's something elegant about nature. Atoms are electrically neutral under normal circumstances. This means the number of electrons orbiting the nucleus equals the number of protons inside it. A hydrogen atom with 1 proton has 1 electron. Oxygen with 8 protons has 8 electrons. This balance is fundamental to atomic stability. So when we talk about elements, we're talking about pure substances made of identical atoms with the same number of protons. Every atom of gold has 79 protons. Every atom of carbon has 6. This uniformity is what makes elements pure and distinct from one another. And it is this atomic number, this count of protons, that determines where each element sits on the periodic table, the great organizing system that reveals the deep patterns hidden within matter itself. This atomic number, this fundamental identity card of every element, became the key that unlocked the puzzle scientists had been wrestling with for centuries. But it took a long time for anyone to realize it. For much of the 1800s, chemists knew that elements existed, and they knew these elements combined in specific ways to create all the compounds around us. They could weigh atoms relative to one another. They could observe how elements behaved when heated, cooled, dissolved, or burned. Yet despite all this knowledge, the elements seemed almost random, a scattered collection with no apparent order or logic. Iron was nothing like oxygen. Sodium behaved completely differently from silicon. Where was the pattern? Did one even exist? Then, in 1869, a Russian chemist named Dmitry Mendeleev had a transformative idea. He decided to arrange the known elements not by their weight alone, but by their chemical properties. He wrote each element on a card and began organizing them into rows and columns, searching for repeating patterns in how they reacted with other substances. What emerged was revolutionary. When he arranged the elements by atomic number in ascending order, the chemical properties repeated in a predictable rhythm. Elements fell naturally into vertical columns, what we now call groups or families, and within each group, the elements behaved remarkably alike. Mendeleev noticed something even bolder. There were gaps in his table, places where an element should exist based on the pattern, but no element had been discovered yet. Instead of assuming he had made a mistake, he predicted what those missing elements should be like. He predicted their properties with astonishing accuracy. Within 15 years, scientists discovered gallium, scandium, and germanium exactly where Mendeleev said they would be, with properties almost identical to his predictions. This wasn't luck. This was a genuine window into the structure of matter itself. The periodic law, the principle that chemical properties repeat periodically when elements are arranged by atomic number, explained why elements in the same group share similar behaviors. Lithium, sodium, and potassium all sit in the first column of the periodic table. They are all soft metals that react vigorously with water. They do this because they all have the same number of electrons in their outermost shell, the electrons most responsible for chemical reactions. One shell, one electron. That single similarity creates a family resemblance that transcends the vast differences in their atomic weights or their positions in the Earth. The same principle applies throughout the table. Fluorine, chlorine, bromine, and iodine form another family, the halogens, all reactive nonmetals with 7 electrons in their outer shells. Helium, neon, and argon are noble gases, chemically inert, because their outer shells are completely full. The periodic table is not a random filing system. It is a map of electron configurations, a visual representation of how atoms organize their electrons, and therefore how they will behave when they encounter one another. Once you understand the law, the table transforms from a confusing grid of symbols into a coherent story about the nature of matter itself. Now that you understand the fundamental logic behind the periodic table, we can learn to read it like a map. And like any good map, it has coordinates. We navigate it using 2 simple directions, across and down. These directions correspond to rows and columns, and chemists call them periods and groups. Periods are the horizontal rows running left to right across the table. There are 7 of them. Each period represents a new shell of electrons being filled. The first period contains only hydrogen and helium, the lightest elements, with just 1 electron shell to fill. By the time you reach period 7, you are looking at the heaviest, most complex atoms we know, with 7 electron shells stacked like layers in a cake. As you move from left to right within a single period, each element has 1 more electron than the one before it. The shells stay the same, but the nucleus grows stronger, pulling those outer electrons tighter. Groups, by contrast, are the vertical columns. There are 18 of them, and they are the true families of the periodic table. Elements in the same group share something profound. They have the same number of electrons in their outermost shell. This is why they behave so similarly. Sodium and potassium are in the same group, and both react violently with water. Chlorine and bromine are in the same group, and both are hungry for electrons. Helium and neon are in the same group, and both are completely unreactive. The group number tells you exactly how many electrons are in that outer shell, the one that determines chemical personality. Within this structure, we find 3 major families of elements that dominate the world around us. The metals occupy the left side and center of the table. They are shiny, they conduct electricity, they bend without breaking, and their electrons are loosely held. Metals want to give away their outer electrons to become positive ions. Iron, copper, gold, aluminum, these are the builders of civilization. the materials we shape into tools and buildings and wires. On the right side of the table, you find the non-metals. They are the opposite of metals in almost every way. They are poor conductors, they are brittle, and their electrons are held tightly. Non-metals want to gain electrons, to become negative ions. Oxygen, nitrogen, carbon, these elements are the foundation of life itself. They form the complex molecules that make up every living thing. Between the metals and non-metals lies a thin, jagged line. This borderland contains the metalloids, elements that cannot decide which family they belong to. Silicon, arsenic, antimony, these are the shape-shifters of chemistry, elements that behave sometimes like metals and sometimes like non-metals, depending on conditions. They are the semiconductors that power our computers and phones, the bridge between two worlds. Understanding these patterns is understanding chemistry itself. The periodic table is not just a reference tool, it is a prediction engine. Once you know where an element sits, you know its family, its personality, its promises, and its limitations. You can predict how it will react, what it will bond with, what role it will play in the grand molecular drama.